Assalamualaikum warahmatullahi wabarakatuh. The first part in this video will explain about the logistic equation. Logistic equation assumes that the density-dependent factors are regulating population growth. Today, this equation has been used widely in many fields. For example, it is used to estimate the emission of carbon dioxide from fossil fuel combustion. And in this video, the logistic equation is used to determine the bacterial biomass as dry wave, cell formation, lactic acid production, and also acetic acid production.
Alright, so for the manual and computer-aided solution, it is the method that we use to calculate the data of head and skin of the red scorpion fish. For the calculation, we use the logistic equation that was shared for the last assignment. For this assignment, the logistic equation are calculated manually and automatically. For manually, we use calculator and jot down the result manually follow 5 decimal point. Plus, manual calculation take a long time to get all the total of the calculation. For your information, this logistic equation used to calculate its biomass, lactic acid bacteria, cell and acetic acid. Next, for the computer-aided solution, the calculation are held automatically as we use the Google Colab and coding. This method required the coding skill to get the result precisely. Then, after the coding, we just plug in the number and run the cell. Then, we got the result. Plus, this computer-aided solution used to justify the manual calculation and make it tally with the result. Hence, the result will be more reliable for this calculation.
This is the last part of video presentation, which is discussion of project. This slide shows the sneak peek of the graph, which I will explain later on. In each logistic equation of the product determined of biomass X, cells G, lactic acid L, and acetic acid A in both figure, the independent variable culture time T is replaced by equal to 1, 2, 3, 4, and up until 20. However, once the population of bacteria becomes high enough, resources become scarce, reducing the pace of development. The product determinant of X, G, L, and A rose gradually and initially, as shown in Figure 1. Because both X and A starting growth rates are minimal, there is an intersecting point at between T equal to 7 and T equal to 10. The reason is because the product's maximal output is low, suggesting a limited carrying capacity K. When the number of bacteria in a colony reaches its K, the rate of growth slows down, and both growth rates of X and A level out. There is also an intersecting point for G and L development between T equal to 15 and 18. Figure 1 also shows a significant rise in L production, making it the greatest production identified. As a result, it creates the greatest bacterial concentration or proliferation. Figure 2 shows the growth rate of X and A has not increased significantly since their initial growth. As the bacteria adjust to their new habitat, the X and A exhibit the lag rates. As the value of the plotted graph shows, just a tiny increase. The growth rate of A continues to rise with a marginal increase. It reveals that A has surpassed the environment's K sooner than the other product identified, which has the slowest growth rate. Over the course of the culture, the growth rate of G and L skyrocketed, intersecting at T equal to 12 and T equal to 15. And the rate of increase of L continues to outpace the rate of proliferation of G. It means the lactic acid bacteria will reach their full potential.
My name is AIMAN and I will present the comparison of lag growth between the marine plankton produced from red scorpion fish, skin and head. Figure 3 shows biomass has a higher production of product determined and a high carrying capacity, so the bacteria can grow in higher concentrations from the skin of red scorpion fish than from the head of red scorpion fish. Aside from that, Figure 4 indicates a larger growth rate in cells from the head of red scorpion fish at the start, but both cells from the skin of red scorpion fish and the head of red scorpion fish attain the same growth rate in the end. Then, Figure 5 shows lactic acid from the skin of red scorpion fish and lactic acid from the head of red scorpion fish both continue develop, with lactic acid from the head of red scorpion fish growing at a faster pace than lactic acid from the skin of red scorpion fish. Lastly, Figure 6 shows acetic acid from the skin of a red scorpion fish grows at a much faster pace than acetic acid from the head of red scorpion fish with a substantial growth rate.